Inelastic collisions and explosions. Here's a cool lab, the Momentum Observation Lab, low-tech, qualitative way for students to observe elastic and inelastic collisions, where the other lab, the Momentum Lab HT Lab, is a high-tech way. A lab sheet, teacher notes, and lab quiz can be found for each by logging into your teacher account and clicking on the lab section of the page linked below. Objects in an isolated system can interact with each other in a number of ways. They can collide. If they are stuck together, they can explode or push apart. In an isolated system, measurements show, and that's very important, this is experimentally proven, that both momentum and total energy are conserved, but the energy can change from one form to another. Conservation of momentum and change in kinetic energy, specific type there of energy, help us predict what happened or what will happen in one of these events. We differentiate between collisions and explosions by the way the energy changes or does not change form. An explosion, we'll deal with that first. An object or objects break apart because potential energy stored in one or more of the objects is transformed into kinetic energy. So here we have the before situation. We have two objects moving together. So the momentum of A plus the momentum of B is equal to their combined mass, m sub A plus m sub B, times the initial velocity. After they move apart, and that's what this little prime sign means, the momentum of A after they explode is the mass of A times the final velocity of A after the explosion. And same thing over here, just for object B. Inelastic collisions. Two objects collide and stick together, converting some kinetic energy into bonding energy, heat, and sound. So here we have two objects moving towards each other, and each one has a momentum. This is momentum A, this is momentum B. Then they hit and stick together. So their final momentum of A and B, since they're combined, they're stuck together, it's the total mass of the two times the final velocity of the two objects. Then we have elastic collisions. Two objects collide and bounce off each other, but here's the big deal. They conserve kinetic energy. That's the big point. In the inelastic collisions, kinetic energy was not conserved. So what we have before, here's again the initial momentum. It looks just like an inelastic collision. They each have their own momentum. They hit and bounce off each other. So they have their own momentum, right? The prime shows the momentum after the collision, and this is the momentum of the other, of object B. But the key here, kinetic energy is conserved. Very valuable table. You'll see this in every level of physics that you take. Now, we discussed the inelastic collision, but we said the objects stick together. Well, we didn't give the whole story. In a general inelastic collision, see we have general here, the objects will still bounce off of each other, okay, just like an elastic collision. Momentum is conserved, but here's the key thing. Kinetic energy is not conserved. That differentiates an inelastic collision from an elastic collision. The perfect inelastic collision is the case we showed, where the objects stick together. So we call that a perfect inelastic. You have one case where the objects bounce off, but the kinetic energy is not conserved. And then you have the perfect case, where kinetic energy once again is converted to some other energy. Potential energy, bonding energy, heat, sound, whatever. However, momentum is conserved there too. You might see a pattern here. Momentum is conserved on all of these. Elastic collision, there they have to bounce off each other. They will not stick to each other. And kinetic energy is conserved. That's the only line on this table where kinetic energy is conserved. And finally, we have an explosion where the object or objects break apart, momentum is conserved, but kinetic energy is not conserved. That could be obvious, right? If the object's just sitting there not moving, it has no kinetic energy. If it breaks apart, each one of the smaller objects will have kinetic energy, so clearly it's not conserved. And one more point. Look at the explosion and the perfect inelastic collision. If you filmed one of them and ran it backwards, it would look like the other guy, right? Because the perfect inelastic, two objects are apart, they come and stick together. The explosion, two objects are together, and then they split. So it's kind of like time reverse between those two.